Right now, at this exact moment. You're hurtling through space at 18 miles per second. That's not a typo. As you're reading this, Earth is racing around the Sun at 67,000 miles per hour. You're traveling 18 miles every single second without feeling a thing. But here's where it gets wild. Light. Light moves at 186,000 miles per second. That's 10,000 times faster than you and Earth combined. And here's the part that'll blow your mind. If you could somehow reach almost light speed, time would start slowing down for you. While 1 year passes on Earth, you'd only age 16 days. But getting close isn't enough. What happens when you hit exactly light speed? Some physicists say time stops. Others say the question doesn't make sense. Some say the entire concept of time breaks down. Today, we're going to answer that question. And I'm warning you, the answer will completely change everything you thought you knew about time. Before Einstein, when time made sense. Let's go back to 1904, before everything changed. Back then, the world was simple. Time was universal. Your time, my time, a star's time, all of it flowed at the same rate. 1 second on Earth meant 1 second on Mars. 1 second in New York meant 1 second in the Andromeda galaxy 2 million light years away. It made perfect sense. It felt right. It matched our everyday experience. There was just one problem. It was completely wrong. Think about it. For thousands of years, humans watched the sun rise and set. We measured time with sundials, water clocks, mechanical clocks. Every civilization came to the same conclusion. Time flows the same for everyone, everywhere. Newton himself declared it in his Principia Mathematica in 1687. He called it absolute time, universal time, time that existed independent of space, matter, or motion. Scientists built their entire understanding of physics on this foundation. It was the bedrock of classical mechanics. Trains, bridges, steam engines, the entire industrial revolution, all calculated using Newton's absolute time. But cracks were appearing. In the late 1800s, scientists were obsessed with light. They knew light was a wave, but waves need something to wave through. Water waves need water. Sound waves need air. So what did light waves travel through? They called it the luminiferous, etherian, invisible substance, filling all of space. Earth had to be moving through this ether as it orbited the sun. Scientists designed experiments to detect it. In 1887, Albert Michelson and Edward Morley conducted the most famous failed experiment in physics. They tried to measure Earth's motion through the ether by comparing the speed of light in different directions. The result? Nothing. Light moved at the same speed in every direction. No matter how Earth moved, no matter what time of year, light speed stayed constant. It broke everything we thought we knew. Einstein's revolution, the paper that shattered reality. 1905. A 26-year-old patent clerk in Bern, Switzerland, published a paper. The title was boring, on the electrodynamics of moving bodies. Nobody paid attention at first. The journal it appeared in wasn't even prestigious. This wasn't some professor at a famous university. This was a guy who spent his days evaluating patent applications for electromagnetic devices. But that paper, it detonated a bomb in physics. Einstein's idea was radical yet simple. What if light speed isn't just constant? What if it's the constant? What if it's the one unchanging thing in the entire universe? Here's what he proposed. Light always travels at 186,000 miles per second. Always. not relative to anything. Just ... always. If you're standing still, light passes you at 186,000 miles per second. If you're flying toward it at 100,000 miles per second, light still approaches you at 186,000 miles per second, not 286,000. That's impossible. You're thinking, yet it seems impossible. It violates common sense. It breaks our intuition about how motion works. But it's true. Think about it this way. When you're on a train going 60 miles per hour and you throw a ball forward at 20 miles per hour, someone on the ground sees that ball moving at 80 miles per hour. Speeds add up. That's how every single thing in our experience works, except light. You're on a spaceship going 100,000 miles per second. You shine a flashlight forward. Classical physics says someone watching from Earth should see that light moving at 286,000 miles per second, but they don't. They see it moving at exactly 186,000 miles per second. The same speed you see it moving inside your ship. This isn't theory anymore. We've measured it thousands of times. Light speed is always the same, regardless of the motion of the source or the observer. So Einstein asked the obvious question: if light speed never changes, what does? The answer: everything else. Space, time, mass, reality itself. Time becomes relative. The universe gets weird. If light speed is constant, time can't be. Let me show you why with the simplest thought experiment in relativity. Imagine you're on a spaceship moving at half the speed of light, 93,000 miles per second. Inside the ship, you point a laser at the ceiling. The light beam goes straight up, hits the ceiling, bounces straight back down. From your perspective inside the ship, this is boring. Light goes up, light comes down, takes, let's say, 1 nanosecond. But now imagine someone watching your ship from outside, floating in space. What do they see? They see your ship racing past at 93,000 miles per second. They see you fire the laser. But from their perspective, that light doesn't go straight up and down, it traces a diagonal path. By the time the light reaches the ceiling, your ship has moved forward. By the time it comes back down, the ship has moved even further. So the light traveled a longer path from the outside observer's viewpoint. A much longer path. But here's the kicker. Light speed is constant. If light traveled a longer distance, but at the same speed, it must have taken more time. More time for them, less time for you. Same event, different amounts of time. Time is relative. This isn't philosophy. This is math. This is physics. This is reality. Einstein gave us a beautifully simple equation. When you're moving slow compared to light speed, time passes almost normally. But as you approach light speed, time stretches, dilates, slows. At half light speed, time moves about 15% slower for you. At 90% light speed, time runs at less than half its normal rate. At nearly light speed, you're experiencing time at just a few percent of normal speed. The faster you go, the slower time flows for you relative to the outside world. The proof: your phone knows Einstein was right. Okay, but this is just theory, right? Nobody actually travels at light speed. Wrong. We test this every single day, and you're carrying the proof in your pocket. GPS, Global Positioning System. Your phone determines its location by communicating with satellites orbiting 12,500 miles above Earth. These satellites are constantly transmitting signals, and your phone calculates your position based on how long those signals take to arrive. But here's the thing: those satellites are moving fast. They orbit Earth at about 8,700 miles per hour. According to Einstein's special relativity, time should move slower for the satellites than for us on the ground. The satellites are moving faster, so their clocks should tick slightly slower, and they do. Every day, the atomic clocks on GPS satellites fall behind Earth-based clocks by about 7 microseconds due to their velocity. 7 millionths of a second, that's nothing, you might say. 7 microseconds of timing error causes about 1.5 miles of position error every single day. If GPS systems didn't account for relativistic time dilation, your navigation would be off by miles within hours. By the end of a week, your phone would think you're in a completely different city. But it doesn't, because the system corrects for relativity. GPS engineers program the satellites to tick their clocks slightly faster to compensate for time dilation. They literally program Einstein's equations into the system. There's also general relativity at play. The satellites are further from Earth's gravity, so time runs slightly faster for them, but the point stands. Time dilation is real, measured, and essential to modern technology. We've also proven it in particle accelerators. Unstable particles that normally decay in about 2 microseconds last 10 times longer from our perspective when we accelerate them to nearly light speed. Their internal clocks are running slow because they're moving so fast. We've sent atomic clocks on airplanes around the world and compared them to stationary clocks. The traveling clocks run slower by exactly the amount Einstein predicted. Time dilation isn't speculation, it's not a mathematical curiosity. It's a fundamental feature of reality that we measure, account for, and depend on every single day. The journey begins, stepping toward light speed. So now we know, time is relative. It slows down when you move fast. Einstein was right. But how slow can time get? What happens when you push closer and closer to light speed? That's what we're about to explore. We're going to take a journey through velocity, starting slow, accelerating harder, pushing toward that ultimate cosmic speed limit. At 10% light speed, time barely changes. At 50%, things get noticeable. At 90%, reality starts breaking down. And at nearly light speed, the universe becomes unrecognizable. We'll watch stars change color. We'll see space itself compress into a single point. We'll witness your mass grow toward infinity and your energy requirements exceed the output of entire galaxies. And through it all, we'll keep asking, what happens at 100%? What happens when you reach light speed itself? Can time actually stop? Or does the question even make sense? Some of you watching this are thinking, time can't stop. That's impossible. Others are thinking, if time stops, what would that even feel like? Here's what I'll tell you. The answer is stranger than both of those guesses. Because at light speed, the universe doesn't just change, the very fabric of physics breaks down. The equations that govern everything stop working. You enter a realm where our normal concepts of space, time, and existence become meaningless. But we're getting ahead of ourselves. First, we need to understand what happens on the way there. We need to see how time slows gradually, how space warps, how mass increases, how light itself shifts and distorts. We need to climb the ladder of velocity, step by step, watching reality transform around us. Ready? Let's accelerate. Part 2. The transition from slow to medium velocities, 10% light speed, where the journey begins. Let's start building your spaceship. Imagine you've done it. Through some incredible breakthrough in propulsion technology, you've built a vessel that can reach 10% of light speed. That's 18,600 miles per second. To put that in perspective, The fastest human-made object ever, Voyager 1, travels at about 38,000 miles per hour. It's been flying since 1977 and it's now over 14 billion miles from Earth, the most distant human-made object in existence. Your ship. It's moving 2,000 times faster than Voyager. At this speed, you could travel from Earth to the Moon in less than 13 seconds. The distance that took the Apollo astronauts 3 days, you cover in the time it takes to read this sentence. You could reach Mars at its closest approach in about 4 minutes. Jupiter, 35 minutes. The edge of our solar system, about 7 hours. This is already insane by human standards. This would revolutionize space exploration. We could send probes to the nearest stars within decades instead of millennia. But here's the shocking part. At this speed, time dilation is barely noticeable. The time dilation factor is about half of 1%. That means if a full year passes on Earth 365 days, you experience about 363 days. You've saved less than 2 days. Less than 2 days per year. At this speed, you could spend a decade exploring the galaxy. And when you returned to Earth, you'd only be about 18 days younger than everyone else. Your friends would hardly notice. Your family might not even believe relativity was real. This is what's so deceptive about relativity. At normal speeds, even speeds that seem incomprehensibly fast by human standards, the effects are minimal. Time dilation exists, but it's subtle, marginal, easy to ignore. But speed is like compound interest. The effects multiply exponentially as you approach that cosmic speed limit. And we're about to see that multiplication begin. 50% light speed, when reality starts shifting. Now you're pushing harder. Your ship's fusion engines roar to life, antimatter reactors pulse with barely contained energy, and you accelerate. 50% of light speed. 93,000 miles per second. At this velocity, you could travel from Earth to the Moon in about 2.5 seconds. From the Sun to Earth 93 million miles in just over 16 minutes. The nearest star system, Alpha Centauri, is about 4 light-years away. At half light speed, you'd reach it in about 9 years by Earth's clocks. But here's where things get interesting. Time dilation at 50% light speed is about 13%. That means when 1 year passes on Earth, you only age about 316 days. You've gained 49 days per year. Think about what that means. After that 9-year journey to Alpha Centauri, Earth has aged nearly 9 years. But you've only aged about 7.5 years. More than a year of difference. Now we're talking. Your body ages slower. Your heart beats the same number of times, but more time passes in the outside universe for each beat. If you left behind a twin on Earth, they'd be noticeably older when you returned. But time dilation isn't the only weird thing happening now. You look out your window and something is wrong with the stars. The Doppler effect. When light changes color, dead ahead, the stars are turning blue, not slightly blue, intensely, unnaturally blue. Stars that should be white or yellow are now radiating deep blue and violet light. Some are even shifting into wavelengths your eyes can't see. Ultraviolet radiation, invisible to human vision, but measurable by your instruments. Behind you, the opposite is happening. Stars are turning red, crimson, dark red. Some are fading into infrared, dropping out of the visible spectrum entirely. To your left and right, the stars look more normal, but even they seem slightly distorted. Welcome to the Doppler effect. You already know this phenomenon from sound. When an ambulance races toward you, its siren sounds higher pitched. As it passes and moves away, the pitch drops. The sound waves compress as the source approaches and stretch as it recedes. Light does the same thing. As you race toward a star at 93,000 miles per second, you're colliding with its light waves at incredible speed. The waves compress, their wavelength shortens, their frequency increases. Short wavelength means blue light. Even shorter means ultraviolet. Shorter still means X-rays. The stars behind you. You're running away from their light. The waves stretch out. Wavelength increases. Frequency drops. Long wavelength means red light. Longer means infrared. Longer still means radio waves. This is your first hint that you're entering light's domain. At low speeds, light seems constant and unchanging. But now you're moving fast enough that light itself behaves differently. You're seeing the universe through a relativistic lens, and the view is starting to distort. But we're just getting started. 90% light speed, where physics gets violent. You keep accelerating. The G-forces are crushing, but somehow your ship's inertial dampeners are working. Hey, this is a thought experiment. We're allowed some engineering magic. 90% of light speed, about 167,000 miles per second. Now we're cooking. At this velocity, our entire solar system from the Sun to Neptune, you traverse it in 6 hours. The distance that takes light 5 hours to cross, you cover in just 1 hour more. The nearest star, you arrive in about 5 years by Earth clocks. But for you, the journey feels like about 2 years. Time dilation has jumped to about 56%. When 1 full year passes on Earth, you experience only 159 days. You're aging at less than half the rate of everyone back home. This isn't marginal anymore. This is dramatic. If you left Earth at age 30 and traveled for 20 Earth years, you'd return at age 39. Your childhood friends would be 50. Your parents might not even recognize you. You'd have become a time traveler, moving into everyone else's future. But that's not even the strangest part. Your mass is increasing. Energy becomes mass. Einstein's most famous equation strikes again. Energy equals mass times the speed of light squared. Most people think this means you can convert mass into energy, which is true, and it's how nuclear bombs and the sun work, but it also works in reverse. Energy can become mass. And right now, you have a lot of kinetic energy. At 90% light speed, the energy required to accelerate you is enormous. And where does that energy go? It becomes part of your mass. Your spaceship, which maybe weighed 100 tons at rest, now has a relativistic mass of about 230 tons. You haven't added any material. You haven't gained any atoms, but you've gained mass about 130 tons of it purely from motion. This is why nothing with mass can reach light speed. As you accelerate, your mass increases. As your mass increases, it takes more energy to accelerate further. The faster you go, the more massive you become, and the harder it is to go even faster. It's a feedback loop that approaches infinity. But we're not talking about infinity yet. At 90%, you're still in the realm of the possible barely, and space itself is starting to break. Length contraction, when space compresses. Look forward through your view screen. Space is squished. The stars ahead of you seem closer together than they should be. Distances in the direction of your travel have shortened. A light year, the distance light travels in a year, measures shorter for you than for someone at rest. This is length contraction, named after the physicist Hendrik Lorentz, who discovered the mathematics before Einstein explained what it meant. At 90% light speed, distances in front of you contract by about 56%. A journey that Earth measures as 10 light-years, you measure as only about 4 light-years. This isn't an illusion. It's not a visual effect. Space itself is compressed in your reference frame. This creates something beautiful and bizarre. You can travel to distant stars in less time than light takes to get there from your perspective. Earth measures your journey to Alpha Centauri as taking about 5 years because you're moving at 90% light speed across 4 light-years. But you measure the journey as about 2 years because, for you, Alpha Centauri is only about 2 light-years away. Different amounts of time, different distances, same journey, and through all of this, light still moves at exactly 186,000 miles per second relative to you. You're moving at about 167,000 miles per second. And yet light from stars ahead of you still approaches at full light speed. It doesn't add up. It stays at 186,000. Light speed is the one constant in a universe where everything else, time, space, mass bends and warps. Which raises the question, what happens when we push even harder? The exponential climb. Why each step gets harder. Here's something that's going to mess with your mind. Getting from 0 to 10% light speed, let's say that requires X amount of energy. Getting from 10 to 50%, that requires about 10 times X energy. Getting from 50 to 90%, about 100 times X energy. Each jump requires exponentially more energy than the last. Why? Because you're fighting against your own increasing mass. Every bit of velocity you gain adds mass, and that extra mass resists further acceleration. It's like trying to push a snowball uphill as it gets bigger. Except in this case, the snowball grows purely because you're pushing it, and it gets worse. At 90% light speed, accelerating further requires incredible energy. To reach 99%, just 9% faster, you'd need to input as much energy as you've already used to get to 90%. Think about that. You've already accelerated to 90% of light speed. You've pumped enormous amounts of energy into your ship. And to gain just 9% more velocity, you need to double your total energy expenditure. This is why light speed is a barrier. Not just difficult, progressively impossible, but let's say you've got fusion reactors, antimatter engines. Maybe you're harvesting energy from a star. You've got power, lots of it. You push harder, the engines scream. Your ship vibrates with barely contained force. And you break through to 99%. 99% light speed. The universe becomes a tunnel. You've done it. 99% of light speed. About 184,000 miles per second. At this velocity, you could circle Earth's equator 7 times in 1 second. The Moon is less than a second away. Mars, at closest approach, 20 seconds. Jupiter, 3 minutes. The edge of the solar system, 4 hours. Time dilation is now about 86%. Earth experiences 1 full year. You experience about 52 days, 7 times slower. If you spent a decade traveling at this speed, you'd age only about 1.5 years while Earth aged 10. Your twin brother on Earth would look like your grandfather when you returned. Your mass has increased by a factor of 7. Your 100-ton ship now has the relativistic mass of about 700 tons. But forget all that for a moment. Look outside. The universe has transformed into a tunnel. Relativistic aberration. Reality's new shape. Every star in the forward hemisphere, billions of stars spread across half the sky, has compressed into a narrow circle directly ahead of you. It's like looking through a telescope, except you're not. All the stars to your front and sides have been gravitationally lensed and Doppler shifted into a cone maybe 30 degrees wide. Behind you, the same thing. Every star in the rear hemisphere compressed into another narrow circle. To your left and right, almost complete darkness. The stars that should be at your sides have been aberrated, forward or backward, empty black stretches across most of your view. This is relativistic aberration, a consequence of moving so fast that even the paths of incoming light rays are distorted. And the colors? Forget what I said about blue and red shifts earlier. That was nothing. The stars ahead are now radiating predominantly in ultraviolet and X-ray wavelengths. White stars look violet. Red stars look blue. But most of the spectrum has shifted beyond what your eyes can detect. Your instruments are going crazy with UV and X-ray radiation. The stars behind you have redshifted into deep infrared and radio wavelengths. You can't see them with your eyes anymore. They've vanished from the visible spectrum entirely. You're flying through a universe that looks nothing like the one you left. And here's the kicker. You feel completely normal. Your heart beats at the same rate. Your thoughts move at the same speed. If you look at a clock on the wall, seconds tick by normally. You're not experiencing anything unusual. It's only the outside universe that's changed. From Earth's perspective, you've been slowed to 1/7 speed, like a video playing in slow motion. But from your perspective, everything's fine. This is what makes relativity so disorienting. There's no absolute reference frame, no God's eye view. Everyone experiences time normally in their own frame. It's only when you compare different frames that the weirdness emerges. But you're not done accelerating, because we need to answer the question, what happens when you push to the edge? When you approach light speed so closely that the difference becomes meaningless? What happens when you get even closer? Crossing into the unknown, where do we go from here? At 99% light speed, you're already experiencing time at 1/7 normal speed. The universe has compressed into twin tunnels of light. Your mass has multiplied 7-fold. But this is nothing compared to what's coming, because the curve of relativity isn't linear. It's exponential, and we're approaching the steep part. That final 1%, from 99 to 100% light speed, contains more weirdness, more distortion, more reality-breaking physics than everything we've covered so far combined. Time dilation will approach 100%. Space will compress to nearly zero. Your mass will explode toward infinity. The energy requirements will exceed the output of stars, galaxies, maybe even the observable universe. And at the very end, when you get impossibly close, we'll confront the ultimate question. Can time actually stop? Some of you are thinking, of course it can. The math says so. Others are thinking, that's impossible. Time can't stop any more than space can disappear. Here's the truth. You're both wrong and both right. And the real answer is more disturbing than either extreme. Because, at light speed, physics doesn't just bend. It shatters. The equations break. The very concepts we're using, time, space, velocity, mass stop, making sense. We're about to enter territory where mathematics leads to infinity, where logic circles back on itself, where the human brain struggles to process what the universe is doing, ready to keep climbing. Because, next, we cross into the extreme speeds, where each additional percentage point requires more energy than the last, where the universe collapses into a single point of light ahead of you, and everything else vanishes into darkness, where time becomes a resource you can stretch like taffy. Let's find out what happens when you get really, really close to the cosmic speed limit. Part 3. Extreme speeds and universal transformation. Nearly light speed, where the universe breaks down. You've pushed beyond 99%. Your engines are running at maximum capacity, consuming more fuel in a second than a small star produces in a year. Now you're incredibly close to light speed. You're only 200 miles per second away from light speed. That sounds like nothing, right? Just 200 more miles per second. Except those 200 miles per second are harder to achieve than the entire journey you've already conquered. Time dilation at this speed is extreme. When one full year passes on Earth, 365 days, you experience only about 16 days. 22 times slower. Think about what this means. You could leave Earth on January 1st, travel through space for what feels like 2 weeks, and return to find everyone celebrating Christmas. Your family has aged a year. You've aged 2 weeks. Your mass, it's increased by a factor of 22. That 100-ton ship now weighs 2,200 tons in relativistic mass. 22 times harder to accelerate. 22 times more energy needed for every additional increment of speed. But mass is the least of your concerns right now. Because when you look outside, the universe has become unrecognizable. The compression of reality. When space collapses, the tunnel effect we saw at 99% has intensified dramatically. Every star, galaxy, and cloud of cosmic dust in front of you has compressed into a tiny circle directly ahead, maybe 4 degrees across. That's about 8 times the width of the full moon from Earth. Billions upon billions of stars, the entire forward hemisphere of the observable universe, squeezed into a space smaller than your fist, held at arm's length. Behind you, the same thing. Earth, the sun, the entire solar system, all the stars you left behind, compressed into another tiny circle. Everything else, pure darkness. Turn your head left or right, and you see nothing. No stars, no galaxies, no cosmic background radiation. Just black empty void stretching in every direction except directly forward and backward. This is length contraction taken to the extreme. Space in the direction of your motion has compressed by over 95%. A light year ahead of you measures only a tiny fraction of a light year from your perspective. You've literally squeezed the universe into a pancake. But it's not just the compression that's disturbing. It's what's happening to the light itself. Radiation hell, when the universe attacks. The cosmic microwave background radiation, the leftover glow from the Big Bang that permeates all of space, normally has a temperature of about 3 degrees above absolute zero. It's cold, harmless. You could bathe in it forever and feel nothing. Not anymore. From your perspective, that radiation ahead of you has been Doppler shifted and blue shifted so severely that it's no longer microwaves. It's not even visible light. It's not ultraviolet. It's X-rays. The entire forward hemisphere is bombarding you with high-energy X-ray radiation. The gentle whisper of the Big Bang has become a roar of deadly particles. Your ship's hull is being sandblasted by radiation that would kill an unprotected human in seconds. Behind you, the opposite is happening. The cosmic background radiation has redshifted so far that it's dropped into radio wavelengths, harmless, long-wave radiation that passes right through you, and the stars ahead have shifted into gamma-ray territory. The most energetic form of electromagnetic radiation known to physics. Each photon carries enough energy to rip molecules apart. You're flying through a universe trying to kill you with its own light. But your subjective experience, still completely normal. Your coffee tastes the same. Your breath comes easy. Time flows smoothly from your perspective. It's only when you look at the monitors showing Earth's telemetry that reality hits you. 22 days have passed for you. Almost a full year has passed on Earth. And you're still accelerating. The exponential wall, energy beyond imagination. Let's talk about what it took to get here. From 0 to 90% light speed, you consumed, let's say, the energy output of a large nuclear power plant running for 1 million years. Enormous, but theoretically achievable. From 90 to 99%, you consumed 10 times that much. The energy output of 10 million power plant years. From 99% to where you are now, that tiny increase in velocity, you consumed another 100 times as much. 1 billion power plant years of energy. And now you want to go faster. To get even closer to light speed, you'd need 10 times more energy than you've already used. 10 billion power plant years. Each increment costs 10 times more than all previous increments combined. This is the exponential wall. This is why light speed isn't just difficult, it's fundamentally impossible for anything with mass. But let's say you've figured it out. Maybe you're harvesting energy directly from black holes. Maybe you've learned to convert matter to energy at 100% efficiency. Maybe you've tapped into the quantum vacuum itself. Somehow, impossibly, you keep accelerating, getting even closer when numbers stop making sense. You push even closer to light speed. You're now only 18 miles per second slower than light. That's roughly the speed Earth orbits the Sun. You're 1 Earth orbit speed away from light speed itself. Time dilation, extreme. When 1 year passes on Earth, you experience about 3.5 days, 100 times slower. A decade on Earth is 5 weeks for you. A century is 1 year. If you traveled at this speed for what felt like a single year to you, Earth would age 100 years. Everyone you know would be dead. Multiple generations would rise and fall while you experienced 12 months. Your mass has increased by a factor of 100. Your ship weighs 10,000 tons in relativistic mass. The universe ahead of you has compressed into a point of light less than half a degree across roughly the size of the Sun as seen from Earth. Everything else is gone. Behind you, Earth and home have shrunk to a similar point. You're in a tunnel of darkness with 2 tiny holes at either end, and you're flying through it at speeds that make mockery of distance. But something else is happening now. Something nobody warned you about. You're having trouble accelerating, not because your engines are failing, not because you're running out of fuel, because you're running into the structure of space-time itself. The cosmic speed limit, why light speed is absolute. Think about what's happening to your mass. At rest, 100 tons. At 90%, about 700 tons. At 99%, about 700 tons. At your current speed, 2,200 tons. Even closer, 10,000 tons. See the pattern. Each time you get closer to light speed, your mass increases dramatically. And it's not just your rest mass, it's your relativistic mass, the mass you need to push to accelerate further. Now extrapolate that pattern. Get even closer. Your mass would be roughly 100,000 tons. Closer still, 1 million tons. Keep going, 10 million tons. And at exactly 100% light speed. Infinite mass, not really big, not incomprehensibly large, mathematically infinite, undefined, a division by 0. Einstein's equations tell us that as velocity approaches light speed, relativistic mass approaches infinity, and to accelerate infinite mass requires ... infinite energy. Not the energy of a star, not the energy of a galaxy, not the energy of the entire observable universe. Infinite energy, which doesn't exist. This is why light speed is the cosmic speed limit. It's not an engineering problem. It's not a fuel problem. It's not a materials problem. It's a fundamental law of physics. The universe itself says no. You can get arbitrarily closer as many decimal places as you want, but you can never reach 100%. Each additional step requires 10 times more energy than all the previous steps combined. Light speed is an asymptote, a mathematical boundary you can approach forever, but never reach. But what if we cheat? What if we ignore reality for a moment and ask, what would things look like if you could get even closer, approaching the impossible edge? Imagine getting closer still. You're now less than 2 miles per second away from light speed. That's fast running speed. You could sprint faster than the gap between your velocity and light speed. Time dilation approaches the maximum. 1 year on Earth equals about 8 hours for you. 1,000 times slower, your mass, 100,000 tons. 1,000 times your original mass. At this speed, you experience a month, while Earth experiences 80 years. You experience a year, while Earth experiences a millennium. Civilizations rise and fall during your coffee break. The universe ahead of you has collapsed into a point of searing gamma radiation, smaller than the period at the end of this sentence. You can't even see it with your eyes anymore. It's pure high-energy physics. Particle soup compressed into a geometric point. Behind you, Earth exists as a mathematical abstraction, a point source of radio waves so faint and stretched that detecting it requires equipment sensitive enough to pick up a whisper from across the galaxy, and the energy required to accelerate even slightly faster. You'd need to harvest multiple stars, not the energy they produce, the stars themselves. Convert their entire mass to pure energy and pump it into your ship. But let's keep going. Let's get even closer. Beyond physical reality, you're now walking speed away from light speed. The gap between you and the ultimate cosmic speed limit is something a human could cover on foot in about 15 seconds, but that gap might as well be infinite. Time dilation approaches maximum. 1 year on Earth equals about 53 minutes for you. 10,000 times slower. You age 1 hour while Earth ages 10 years. You age 1 day while civilizations collapse and new ones emerge. You age 1 year while humanity as a species might evolve into something unrecognizable. Your relativistic mass, 1 million tons. The energy to reach this speed, you'd need to convert the mass of a large planet directly into kinetic energy. Jupiter's entire mass, completely annihilated, might be enough. And to go faster, to get even closer, you'd need the energy equivalent of a small star, not its lifetime output. Its entire mass energy, converted with perfect efficiency and pumped into acceleration. This is where physics stops being science and starts being philosophy. Because at this point, we're not asking, can we build a ship that goes this fast? We're asking, does it even make sense to talk about going this fast? The observer's paradox. Who's really moving slow? Here's something that'll hurt your brain. From Earth's perspective, you're moving incredibly fast, and time is slowing down for you. You're aging at 1/10,000th normal speed. You're experiencing time in slow motion. But from your perspective, time is flowing normally. You're not in slow motion at all. It's Earth that's in fast motion. You look at the telemetry feed from Earth and everyone is moving like a video on fast forward, 10,000 times faster than normal. They're born, they live, They die in what seems like hours to you. So who's right? Who's actually moving slow? Both of you, neither of you. The question doesn't make sense. This is the heart of relativity. There's no absolute reference frame, no cosmic clock ticking away true time. Every observer experiences time normally in their own frame, and every observer sees other frames as time dilated. You see Earth's time as accelerated. Earth sees your time as decelerated. Both perspectives are equally valid. Both are true in their own reference frames. The universe doesn't have a God's eye view. There's no objective reality standing outside all reference frames. Reality itself is relative. This is why Einstein called it the theory of relativity, not because everything is relative in some hand-wavy philosophical sense, but because the measurements you make of time, distance, simultaneity, mass depend fundamentally on your state of motion. But we're still not done, because there's one more region to explore, one final zone before we hit the absolute barrier, the zone where you get impossibly close, the asymptotic approach. Imagine getting closer and closer, adding more and more energy. What happens here? Mathematically, time dilation approaches 100%. Your experienced time approaches 0 relative to Earth. Your mass approaches infinity. The universe ahead compresses to a mathematical point with 0 dimension. The energy needed for further acceleration approaches infinity. Every quantity either goes to 0 or infinity. The equations fill with undefined terms. Division by 0, infinity minus infinity, mathematical singularities. This is the asymptote, the unreachable limit. You can get as close as you want, impossibly, unimaginably close, and you still haven't reached 100%, because there's always another step to take, always another decimal place, always a gap, no matter how microscopically small, between your speed and light speed. And that gap, it requires infinite energy to close. This is why particles in accelerators never quite reach light speed. We can push protons incredibly close, but that final gap is impossible. The last fraction requires more energy than exists in the observable universe. Light speed isn't a speed you reach by going fast enough. It's a mathematical boundary written into the fabric of reality. A cosmic law that says, this far and no further. But that raises the ultimate question. The question we've been building toward this entire time. What if, somehow, impossibly, you did reach 100%? What if you became light itself? What would happen to time? Would it stop? Would it become meaningless? Would you cease to exist? The answer is stranger and more profound than you can imagine, and we're about to find out what it is. Because next, we're going to look at the universe from a photon's perspective. We're going to ask what it's like to be light. We're going to explore what happens at the edge of physics, where the equations break and reality itself becomes undefined. Are you ready to cross the final threshold? Part 4. Approaching light speed and the physical wall. The mathematical barrier, why 100% is impossible. Let's confront the hard truth. Everything we've discussed so far, the journey from 10% to nearly light speeds, technically possible, difficult, absolutely, beyond our current technology, without question, but not forbidden by physics. Reaching exactly 100% light speed, that's forbidden. Not really hard, not we don't have the technology, yet forbidden, impossible, a cosmic law as absolute as the law against traveling backward in time or creating energy from nothing. Here's why. Einstein's time dilation equation has a problem at light speed. When your velocity equals light speed, you end up dividing by 0. And you can't divide by 0. It's undefined. The equation breaks. The same thing happens with the mass equation. At light speed, your relativistic mass becomes infinite. Infinite mass means infinite energy required to accelerate. And infinite energy doesn't exist in our universe. This isn't a practical limitation. This is the universe saying the question itself is wrong. You can't reach light speed with mass because the very concept violates the mathematical structure of space-time. But let's push this thought experiment to its absolute limit. Let's explore what the equations tell us happens as you get impossibly, absurdly close to that barrier. The final steps, approaching the impossible. Imagine you've somehow acquired the energy output of multiple galaxies. You're channeling the power of 1 billion stars into your engines. You're converting entire planets into pure thrust. You push incredibly close to light speed. Time dilation becomes extreme. 1 year on Earth equals about 6 minutes for you. That's not a typo. Earth ages an entire year, 365 days, 8,760 hours, while you age 6 minutes and 20 seconds. You could eat breakfast, and by the time you finish your coffee, a year has passed on Earth. Everyone you know is a year older. Seasons have changed. Birthdays have passed. Wars might have started and ended. Your mass, 10 million tons. 100,000 times your original mass. The energy to reach this speed exceeds the total energy output of our Sun over its entire 10 billion year lifetime. You've consumed more energy than Sol will produce from its birth to its death, and you want to go faster. Get even closer to light speed. Time dilation, 1 year equals about 38 seconds. The Earth experiences 12 months, while you experience less time than it takes to tie your shoes. A century passes in an hour. A millennium in half a day. Your mass, 100 million tons. The energy required. You'd need to harvest multiple stars, not their energy output, their entire mass energy. Convert entire solar systems into kinetic energy. This is beyond comprehension, beyond imagination. We're talking about energies that dwarf anything humanity has ever produced by factors of trillions. And we still haven't reached light speed, climbing the infinite ladder. Let's go further. Get even closer. 1 year on Earth equals about 4 seconds for you. You could count 1 Mississippi, 2 Mississippi, 3 Mississippi, and a full year has passed on Earth. Your heart beats 4 times. 1 year gone. Get closer still. 1 year equals less than half a second. Less than half a second. A blink. Closer. 1 year equals faster than you can snap your fingers. Even closer. 1 year equals faster than a hummingbird's wing beat. See the pattern? Each additional step closer makes you 10 times slower from Earth's perspective, or, from your perspective, makes Earth 10 times faster. Get infinitely close and time dilation approaches, but never reaches 100%. Earth's time approaches infinite speed relative to you. Your time approaches 0 relative to Earth. Your mass approaches infinity. The universe ahead compresses toward a mathematical point with 0 spatial extent. Everything goes to extremes. Everything approaches limits. But nothing ever actually reaches those limits. Because there's always another step to take. Always another decimal place. Always a gap between you and light speed, no matter how many resources you pour into closing it. This is the asymptote, the unreachable horizon, the mathematical wall built into the universe itself. But here's the disturbing question. If you can never reach light speed, What about things that are already at light speed? What about light itself? The photon's journey. Life at light speed. A photon is born in the core of the sun. Nuclear fusion in the sun's center creates high-energy gamma rays. These gamma rays bounce around inside the sun, getting absorbed and re-emitted, scattering through dense plasma for tens of thousands of years before finally reaching the surface. Then, finally, a photon escapes. It breaks free from the sun's surface and races outward at light speed. 8 minutes and 20 seconds later, from Earth's perspective, that photon reaches our planet. It enters Earth's atmosphere, passes through the air, and strikes your retina. You see sunlight. For you, that photon's journey from sun to Earth took 8 minutes and 20 seconds. For the photon, 0 time. Not a very short time. Not almost 0. Exactly 0. From the photon's reference frame, we can even call it that it was created and destroyed in the same instant. The photon experiences no time between its emission from the sun and its absorption in your eye. The journey that takes 8 minutes from Earth's perspective takes 0 time from the photon's perspective. How is this possible? Time at light speed, the equation's answer. Let's think about what happens when we try to plug light speed into the time dilation equation. For a photon moving at light speed, we end up dividing by 0. Undefined. But look at what happens as we approach light speed from below. As velocity gets closer and closer to light speed, the time dilation factor gets bigger and bigger. As it approaches infinity, time passage approaches 0. Infinite time dilation means 0 time passage. From the photon's perspective, the universe in its direction of travel has contracted to 0 length. Distance equals 0. Time equals 0. The photon's birth and death are simultaneous. A photon created in the Andromeda galaxy 2.5 million light-years away experiences 0 time during its 2.5 million year journey to Earth. From its perspective, it travels 0 distance in 0 time. Every photon that's ever existed has experienced exactly 0 subjective time. The light from distant quasars billions of light-years away. The cosmic microwave background from the edge of the observable universe, all of it experiences no time at all. Photons don't age. They don't have a journey from their own perspective. They simply exist at their point of emission and point of absorption simultaneously. This is what it means to move at light speed. Time stops. Space vanishes. The universe becomes a single point. But here's the critical question. Does this mean time stops at light speed? 3 different answers to one question. Ask a physicist, does time stop at light speed? And you'll get 3 different answers depending on who you ask. Answer 1, yes, time stops. The mathematical answer, look at the equation. At light speed, time dilation becomes infinite, which means time passage becomes 0. Time stops. Question answered. This is technically correct from a mathematical standpoint. The equations clearly show that as velocity approaches light speed, experienced time approaches 0. But this answer has a problem. It assumes you can be at light speed, which, as we've established, is impossible for anything with mass. Answer 2. The question is meaningless. The physicists answer, special relativity requires a valid reference frame, and there is no valid reference frame at light speed. The equations break down. You're dividing by 0, which produces undefined results, not infinite results. Asking what's time like at light speed is like asking what's north of the North Pole. The question seems reasonable, but it's based on a faulty premise. There is no north of the North Pole because north is defined relative to the North Pole. Similarly, There's no reference frame at light speed because reference frames are defined relative to light speed. The question is malformed. It doesn't have an answer because it's not actually a valid question. Answer 3. Time doesn't stop becomes undefined. The deeper answer, at light speed, both time and space transform in ways that make our usual concepts meaningless. Time doesn't stop like a paused video. Instead, the entire framework of space-time breaks down. Length contraction, says space, in the direction of travel contracts to zero. Time dilation, says time stretches to infinity. When you multiply zero spatial distance by infinite time, you get ... what? An undefined mathematical expression. A singularity in the equations. The universe at light speed isn't frozen, it's undefined. The laws of physics as we understand them cease to apply, so which answer is correct? The real answer, why the question fails. Here's the truth that reconciles all three answers. You can't reach light speed if you have mass. That's not a technological limitation. That's a law of physics, as fundamental as the conservation of energy. Only things that have zero rest mass can travel at light speed. Photons, gluons, gravitons, if they exist, massless particles that must always travel at light speed and can never travel slower. Everything else, electrons, protons, atoms, molecules, spaceships, humans, has mass, and anything with mass cannot reach light speed. So asking what happens to time when I reach light speed is like asking what happens when I divide by zero, or what color is a square circle. The question contains an impossibility within it. But here's what we can say. As you approach light speed, time slows down for you relative to the outside universe. It gets slower and slower, approaching zero, but never reaching it. From the outside universe's perspective, your time approaches a stop. You age slower and slower, approaching but never reaching zero aging rate. From your perspective, time flows normally, but the outside universe speeds up. Earth ages faster and faster, approaching but never reaching infinite speed. And for photons, which exist only at light speed, they experience no time. But they're not experiencing anything because they have no consciousness, no internal states, no way to measure their own existence. A photon doesn't know it's traveling. It doesn't feel time passing or not passing. It simply is. The practical limit, where real physics stops. Let's bring this back to reality. The fastest speed ever achieved by humans is the Parker Solar Probe, traveling at about 120 miles per second, less than 0.1% of light speed. At this speed, time dilation is completely negligible, less than 1/1,000,000%. The fastest particles ever created in laboratories are protons in the Large Hadron Collider, reaching incredibly close to light speed. At this speed, the protons experience significant time dilation, which is why unstable particles last longer in accelerators than they do at rest. But even at these extreme speeds, we're nowhere near the actual limit. Could we ever build a ship that reaches even 10% light speed? Maybe. It would require either antimatter rockets, fusion drives, or some technology we haven't invented yet. But it's theoretically possible. Could we reach 50%? Much harder. The energy requirements are enormous, but not physically forbidden. Could we reach 90%? Now we're talking about energies that exceed anything human civilization has ever produced. We'd need to harvest stars, tap into black holes, or discover entirely new physics. Could we get to nearly light speed? You'd need the energy output of multiple galaxies, practically impossible with any technology we can currently imagine. Could we get even closer? You'd need to convert entire galaxies into pure energy. This borders on physically impossible even in theory, and 100%, absolutely, fundamentally, mathematically impossible. So where does that leave us? The real cosmic speed limit. What we actually know. Here's what we know for certain. Light speed is absolute. It's the one constant in the universe. Everything else, time, space, mass, energy, is relative. But light speed is always 186,000 miles per second in a vacuum, regardless of who's measuring it. Nothing with mass can reach light speed. The energy required approaches infinity. Your mass approaches infinity. The math breaks down. It's not possible. Time slows down as you approach light speed. This isn't theory, it's observed, measured, proven. GPS satellites, particle accelerators, atomic clocks on airplanes. We've tested it thousands of times. Time dilation is real and dramatic near light speed. The closer you get, the slower time flows for you relative to everyone else. The effect is real. But time never stops, because you never reach light speed. You can get arbitrarily close, but there's always a gap. And that gap means time always flows, even if extraordinarily slowly. The universe has a speed limit, and that limit is enforced by the structure of space-time itself. But this raises one final, fascinating question. If humans could somehow travel incredibly close to light speed, impossibly close to the limit, what would that journey be like? What would it mean to step aboard a ship, travel for 10 years of your subjective time, and return to find Earth aged 100,000 years? Would humanity still exist? Would the sun still shine? Would Earth itself survive? This is time travel. Not backward, but forward. One direction only. Irreversible. And it's actually possible in theory. Time travel. The one-way ticket to tomorrow. Imagine this scenario. You board a spacecraft capable of reaching incredibly close to light speed. Time runs 10,000 times slower for you than for Earth. You decide to explore the galaxy. You accelerate to maximum velocity and spend 10 years from your perspective visiting distant star systems. 10 years for you, 100,000 years for Earth. When you return, you're 10 years older. But Earth has aged 100,000 years. The year you left was 2025. The year you return is 102,025 AD. What would you find? Humanity might be gone, extinct, evolved into something unrecognizable, or spread across the galaxy. The continents would have shifted. The climate would be unrecognizable. Even the stars in the sky would be in different positions. Everyone you knew, every friend, family member, colleague would have been dead for almost 100,000 years. The civilization you left would be ancient history. Your language might be indecipherable. Your culture might exist only in archaeological records, if at all. You would be a time traveler. Not by moving backward, but by skipping forward through everyone else's timeline while experiencing very little time yourself. This is the only form of time travel that physics allows. Forward, not backward. One way, not reversible. And the cruel joke, you'd be awake for all of it. 10 subjective years of your life, watching Earth recede behind you, knowing that every day you travel is 27 years back home. Every year is 10,000 years. You could never go back. Even if you turned around immediately, another 100,000 years would pass. Time travel is possible. But it's also a one-way exile from everything you've ever known. The ultimate question: what happens at the edge? We've climbed the ladder of velocity. We've pushed from 10% to incredibly close to light speed. We've seen time slow, space compress, mass increase, and reality distort beyond recognition. But we still haven't answered the fundamental question: what happens at exactly 100% light speed? Not nearly there, not arbitrarily close, exactly 100%. Does time stop? Does it become meaningless? Does the universe collapse to a point? Do you cease to exist? The answer is both simpler and more profound than you might expect. And in our final section, we're going to explore it. We're going to look at what physics actually tells us happens at the boundary. We're going to examine why the question itself might be flawed. And we're going to discover what this all means for our understanding of time, space, and reality itself. Because the answer to does time stop at light speed isn't just about physics. It's about the nature of existence. It's about what it means to experience reality. It's about the fundamental structure of the universe we inhabit. Are you ready for the final answer? Part 5. The Photon Perspective and Philosophical Conclusion. Living as light, the photon's impossible reality. Let's step into the impossible. Imagine, just for a moment, that you could somehow transform into a photon. Your atoms disassemble, your mass vanishes, and you become pure light, racing through space at the ultimate cosmic speed. What would you experience? Nothing. Not very little. Not things moving incredibly fast. Nothing at all. From the photon's perspective, if such a thing can even be said to exist, there is no journey, no passage of time, no distance traveled. A photon created in the heart of a star, 10 billion light years away, experiences the exact same thing as a photon created 1 millimeter from your eye. Instantaneous existence from birth to death. Think about what this means. That ancient photon has been traveling through space for 10 billion years. From our perspective, it crossed galaxies. It passed through clouds of cosmic dust. It bent around gravitational fields of black holes. It witnessed the birth and death of solar systems. But from the photon's perspective, it was created and destroyed in the same instant. No time elapsed. The universe in its direction of travel contracted to zero width. The 10 billion light-year journey had zero length. Birth and death, simultaneous. This is the strange reality of existing at light speed. You don't experience the journey because there is no journey. Space contracts to nothing. Time dilates to nothing, and the entire universe becomes a single mathematical point. But here's the critical insight. Photons don't experience anything. They have no consciousness, no internal clock, no memory, no awareness of their own existence. A photon doesn't know it's traveling. It can't know because knowing requires time, and photons don't experience time. So when we ask what's it like to be light, we're asking a question that doesn't have an answer, not because we lack information, but because the premise is flawed. The three perspectives, reconciling the impossible. Let's revisit those three answers to our central question. Does time stop at light speed? Now we can understand why each one is both right and wrong. Perspective 1. Time stops the mathematical view. The equations clearly show infinite time dilation at light speed. From the outside observer's viewpoint, a clock moving at light speed would be frozen. Time stops. This is mathematically correct. If you could observe something moving at exactly light speed, you would see its clock stopped, its processes frozen, its internal time stationary. But there's a catch. Nothing with mass can reach light speed to be that something, and things without mass photons don't have clocks to stop. They don't experience time to begin with. So yes, time stops, but only in a mathematical sense that doesn't correspond to any physical reality we can observe or experience. Perspective 2. The question is meaningless. The relativity view. Special relativity requires valid reference frames. A reference frame is essentially a coordinate system with synchronized clocks that allows you to measure positions and times of events. But at light speed, you can't construct a valid reference frame. The transformation equations, which tell you how to convert measurements between reference frames, break down. You get division by zero, undefined expressions, mathematical singularities. Asking what is time like for something at light speed is like asking what color is jealousy, or how much does justice weigh. The question mixes categories that don't connect. Time is defined within reference frames, and there is no reference frame at light speed. So the question isn't just hard to answer, it's not even properly formulated. It's a category error disguised as a physics question. This is probably the most intellectually honest answer. But it's unsatisfying, isn't it? It feels like a dodge. Perspective 3. Time becomes undefined. The deeper view. At light speed, both time dilation and length contraction reach their extremes. Time stretches to infinity. Space contracts to zero. But what does it mean to multiply infinity by zero? What's the product of infinite time and zero space? Mathematics says undefined, not infinite, not zero, undefined. This is different from saying we don't know. Undefined means the operation itself doesn't make sense. It's like asking what's north of the North Pole or what happened before time began. The question contains an internal contradiction. At light speed, the concepts of space and time don't just reach extremes, they break down entirely. The universe doesn't become frozen or compressed. It becomes something our mathematical framework can't describe. This is the deepest answer. At light speed, our normal concepts fail, not because we're ignorant, but because those concepts are built on assumptions that don't hold at light speed. So which perspective is correct? All of them? None of them? They're different ways of describing the same fundamental truth. Light speed is a boundary where physics as we know it ceases to apply. The boundary between matter and energy. Here's what's really happening at light speed. There's a fundamental divide in the universe between two types of things. Things with mass, electrons, protons, atoms, molecules, people, planets, stars. Everything you can touch, see, or feel. These things experience time. They have reference frames. They can move at different speeds from stationary to arbitrarily close to light speed, but never reaching it. Things without mass, photons, gluons, gravitons, pure energy. These things must move at light speed. They can't move slower. They don't experience time. They don't have reference frames. The boundary between these categories is light speed itself. It's not a speed you can reach by accelerating. It's a fundamental divide in the types of entities that can exist. It's like the difference between matter and antimatter, or positive and negative numbers. You can't gradually transition from one to the other, you either are one or the other. Mass-bearing particles move slower than light and experience time. Massless particles move at light speed and don't experience time. There's no middle ground. This is why you can't accelerate to light speed. It's not about having enough energy. It's about changing your fundamental nature from thing with mass to thing without mass. And you can't do that by pushing harder. To reach light speed, you'd have to completely shed your mass. But if you did that, you wouldn't be you anymore. You'd be energy, radiation, a photon. And photons don't think, don't feel, don't experience. So the question, what would happen to time if I reached light speed, contains a hidden impossibility. The eye would cease to exist. The real mystery, why does light speed exist? Step back for a moment and think about how weird this is. Why does the universe have a speed limit at all? In Newtonian physics, there was no maximum speed. You could accelerate forever, getting faster and faster without limit. Add enough energy and you could reach any speed. But our universe doesn't work that way. There's a hard cap, 186,000 miles per second. Nothing goes faster. Why? Why does light travel at exactly that speed and not some other speed? Why is that number the cosmic speed limit? The honest answer is, we don't know. We can measure light speed. We can show that it's constant. We can prove that it's the maximum speed. But we can't explain why it has the value it does or why it acts as a limit at all. It's a fundamental constant of nature, like the charge of an electron or the strength of gravity. These are numbers we measure but can't derive from first principles. But here's what we do know. The existence of a maximum speed is intimately connected to the structure of space-time itself. In Einstein's theory, space and time aren't separate things. They're woven together into a four-dimensional fabric called space-time. Events don't just have a location in space and a separate moment in time, they have a single location in space-time. And in space-time, the speed of light isn't really a speed in the normal sense. It's more like a conversion factor between space and time. It's the number that tells you how much spatial distance equals how much temporal duration. Light speed is the speed at which the spatial dimensions and temporal dimension connect. It's the pivot point of space-time itself. This is why it's absolute. This is why nothing can exceed it. It's not a speed limit like a highway speed limit where you could go faster if you had a better engine. It's built into the geometry of the universe. And this is why time dilation and length contraction exist. They're not strange side effects. They're necessary consequences of space-time having this structure. You can't exceed light speed for the same reason you can't travel to a location that's north of the North Pole. The universe's geometry doesn't allow it. Time travel revisited, the only way forward. So we've established that you can't reach light speed, but you can get very, very close. And that means time travel one direction only is theoretically possible. Let's imagine the scenario one more time, but now with full understanding. You board a spacecraft through some incredible technology, maybe a photon drive that converts matter to pure thrust. Maybe a warp drive that bends space-time itself. You accelerate to incredibly close to light speed. You decide to explore the galaxy for what feels like 10 years to you. You visit distant nebulae, orbit black holes, study alien worlds if they exist. During your journey, time runs 10,000 times slower for you than for Earth. 10 years for you equals 100,000 years for Earth. What would that journey actually be like? Inside your ship, everything seems normal. You eat, sleep, think at normal speeds. You age normally. Your ship's clock ticks at 1 second per second, but when you look out the window, the universe is chaos. Stars born and die in what seems like years. Galaxies rotate visibly. Cosmic events that should take millions of years play out in fast forward before your eyes. If you could somehow maintain a video link with Earth, you couldn't. But imagine you'd watch humanity's entire future unfold like a time-lapse film. Civilizations rise and fall. Ice ages come and go. Continents drift. The sun grows larger and hotter as it ages. All of this happens in what feels like a decade for you. And then you return. You slow down, decelerate, and finally come to rest, relative to Earth. The year is 102,025 You're only 10 years older. Earth has aged 100,000 years. Everyone you knew is gone. Not just dead, forgotten, ancient history. There might be records of your departure in museums or archives, but you'd be mythology by now. The language might be incomprehensible, the culture unrecognizable. Technology would be either incredibly advanced or, if civilization collapsed, primitive again. You'd be a stranger in a strange world, a visitor from the distant past, arriving in what is, to you, the far future. This is real time travel. Not science fiction, not fantasy. A genuine consequence of relativity that's mathematically proven and experimentally verified. The catch: it only works in one direction, forward. You can skip ahead in time, but you can never go back. And it requires energies we can't currently imagine producing. But it's not forbidden by physics. Would you take that journey? Would you sacrifice everything, everyone you know, your entire civilization, your entire era for the chance to see the future? Some would say yes, the chance to witness humanity's destiny, to see how the story ends, to explore the far future might be worth the cost. Others would say no, the loss would be too great. You'd gain the future but lose the present. There's no right answer. But the choice is theoretically available. What we've learned, the nature of time itself. Let's step back and look at the big picture. What have we learned from this journey through velocity? Time is not universal. The most important lesson: your time and my time can run at different rates. There's no cosmic clock ticking away true time. Every observer's time is equally valid. Light speed is absolute. It's the one constant in a universe where everything else is relative. It's 186,000 miles per second for everyone, regardless of their motion. Nothing with mass can reach light speed. This isn't a technology problem. It's a fundamental law. The energy required approaches infinity. Your mass approaches infinity. The math breaks down. Time dilation is real. We've proven it thousands of times. GPS satellites, particle accelerators, atomic clocks, relativity works. The effects are small at normal speeds but become dramatic near light speed. Time travel to the future is possible. If you could reach velocities close to light speed, you could effectively skip forward through time. You'd age slowly while the universe ages normally. One-way ticket to tomorrow. Photons experience zero time. Things that move at light speed don't have a journey from their perspective. Birth and death are simultaneous, but they don't experience anything because they're not conscious. The question, does time stop at light speed, is flawed. Time doesn't stop. The framework of time breaks down. You can't reach light speed with mass, and things without mass don't experience time. The question contains an impossibility, but there's a deeper lesson here, a philosophical one. Time isn't what we thought it was. For thousands of years, humans believed time was like a river flowing at a constant rate, carrying everything along together. Newton codified this as absolute time that exists independently of anything else. Einstein showed us that was wrong. Time is more like a personal experience. It flows at different rates depending on your motion and position in a gravitational field. It's interwoven with space into a unified spacetime fabric. Your time is real. My time is real. But they're not the same time. We each carry our own personal clocks, and those clocks can tick at different rates. This is both liberating and terrifying. Liberating because it means time is more flexible than we thought. Terrifying because it means there's no universal now. Events that are simultaneous for me might not be simultaneous for you. The universe doesn't have a universal timeline. It has billions and billions of personal timelines, one for each observer, all equally valid, all running at potentially different rates. The final answer: time at light speed. So here it is, the answer to the question we started with. Does time stop at light speed? For things with mass, the question is meaningless because they can't reach light speed. You can approach it arbitrarily closely, making your time arbitrarily slow relative to others, but you never reach zero time flow because you never reach light speed. For photons, they don't experience time, but not because time stopped. They exist outside the framework where time is defined. They're born and die simultaneously from their own perspective, but they don't have a perspective because they lack consciousness. From an outside observer, something moving at light speed appears frozen in time. Its clock stops, its processes halt, but nothing with mass reaches light speed, so this is a theoretical situation that never actually occurs. The real answer is this: time doesn't stop at light speed. Time becomes undefined. The mathematical framework breaks down. The concepts we use to describe time reference frames, simultaneity cause and effect cease to apply. Light speed isn't a speed you can reach. It's a boundary between two types of existence, things that experience time and things that don't, and that boundary is absolute. Looking forward, what this means for humanity. Right now, as you read this, you're moving through space at 18 miles per second as Earth orbits the Sun, and somewhere in the universe, perhaps in a distant galaxy, there might be particles racing through space at nearly light speed, experiencing time at 1,000th hour rate. And right now, photons are streaming past you from every direction, from the Sun, from distant stars, from the cosmic microwave background, all of them experiencing zero time as they've done for the billions of years they've been traveling. Time is relative. Einstein was right. If humanity ever reaches the stars, if we ever build ships capable of relativistic speeds, time will become a resource, something we can stretch, something we can manipulate. Want to reach distant galaxies? Accelerate to nearly light speed. A journey that takes 100 million years from Earth's perspective takes only 1 million years from yours. Still a long time, but manageable across generations. Want to see the far future? Travel at extreme relativistic speeds. Skip forward through everyone else's timeline while experiencing minimal time yourself. But you can never go back. Time's arrow points in only one direction. Forward, always forward, and you can never reach the ultimate limit. Light speed will always remain just out of reach, a horizon you approach but never cross. This is the universe we live in, a universe where time is flexible but never stops, where light speed is absolute, where the past is fixed but the future is open. A universe more strange and beautiful than our ancestors ever imagined. The end of the journey, where we stand. We started this journey asking a simple question: what happens to time at light speed? We've traveled from 10% light speed to incredibly close to it. We've watched time slow from barely noticeable to nearly stopped. We've seen the universe compress from a sphere to a tunnel to a single point. We've witnessed mass increase from normal to nearly infinite, and we've discovered that the question itself was more complicated than we realized. Time doesn't stop at light speed. Instead, the entire concept of time transforms into something our normal language can't describe. The equations break down. The framework fails. We reach the edge of what physics can tell us. But that's okay. That's how science works. We push understanding as far as it will go, and when we hit a boundary, we learn something profound about the structure of reality. The boundary at light speed teaches us that time and space aren't fundamental. They're emergent properties of something deeper, space-time itself. And at light speed, we're seeing the seams where our normal concepts no longer apply. Einstein gave us the tools to understand this. Relativity showed us that time is relative, light speed is absolute, and the universe is far stranger than our intuition suggests. And now you understand it too. The next time someone asks you, does time stop at light speed? You can give them the real answer. Time doesn't stop because nothing with mass can reach light speed. But if it could, time wouldn't stop, it would break. The question itself reveals the limits of our understanding. Light speed isn't a destination. It's a boundary, a wall built into the fabric of space-time itself. And on this side of the wall, time flows. Slow or fast, stretched or compressed, but always flowing, 1 second at a time. Whether that second takes an hour on Earth, or a year or a century, it's still 1 second for you. And that's the most important lesson of all. Your time is real. Your experience is valid. No matter how fast you move, you always experience time at 1 second per second. The universe may be relative, but your existence is absolute. Thank you for joining me on this journey through space-time. May your future, however fast or slow it arrives, be filled with wonder.